Hey everyone, it's Professor Pemberton. In this video we're going to look at optimization problems. So the methods that we discussed so far in this chapter for finding extreme values have practical applications in many areas of life. In this section we're going to look at how does the first and second derivatives help us solve a variety of optimization problems from business, math, physics, and economics. So we're going to look at how to solve applied problems involving optimization of area, perimeter, volume, distance, and marginal analysis in economics. So optimization problems. In solving practical problems, one of the greatest challenges in solving optimization problems is how do you convert the word problem into a mathematical optimization problem where you find a function that you are trying to maximize or minimize. And that's what it means to optimize the function. So we're going to go through these 6 steps on how to solve optimization problems. The first step is always to read the problem carefully and always ask yourself, what is unknown in the problem? What are the given quantities in the problem? And then, are there any given conditions in the problem? Once you've read the problem, it always helps to draw a diagram because most of the problems will involve area, perimeter, volume, or surface area. So draw a diagram. Identify the given and required quantities. So in your diagram, label what's unknown and what is given. Introduce the notation, so assign variables or symbols to quantities that need to be maximized or minimized, and also select symbols for unknown quantities, and also label the diagram. And it might help to use initials that are suggestive of what the variable represents. So distance, you would probably want to use a D, area, probably a capital A, volume, a V. Step 4, you have a function that needs to be maximized or minimized. Try to have the function related in terms of some of the other symbols or variables from the last step. If the function is maximized or minimized, it can be expressed, typically it will be expressed in terms of more than one variable. If it is, then you need to use additional information in the problem that relates the several variables together and use those equations to eliminate all but one of the variables in the function. So you need to have a function of just one variable. And this is not the same type of problems as related rates. Related rates were always functions of time. There is no change in time in these problems. So we want the function to be in terms of only one variable. And then we'll get to the calculus step, which is the last step. Use methods discussed in this chapter. What that means is you can use the closed interval method to find the absolute maximum and absolute minimum value of the function. And keep in mind, the function needs to be defined on a closed interval, and the function must be continuous, to use the closed interval method or the extreme value theorem. So we're going to start with 2 very simple problems. You probably have seen these problems from pre-calculus, but we're going to get an idea of how to use the optimization steps, how to find the absolute maximum and absolute minimum for these 2 problems. So example 1 says, suppose that you have a farmer with 2,400 feet of fence. They want to fence off a rectangular region or area, and one of the sides faces a straight river, so the farmer needs no fence for that side. What are the dimensions of the field that will give you the largest area, and what is the largest area? So I said that you would probably have seen this before in pre-calculus because this function that we're going to maximize turns out to be a quadratic function. So here are the steps. So first step is to Identify what is unknown in the problem. So let x denote the width of the rectangular area. And we'll let y denote the length. Be very descriptive of what the variables represent. Both the length and the width are measured in feet because the 2,400 is measured in feet. Notice that if you add these three sides of your diagram, so width, and then one length because the other side is facing the river, the perimeter is 2x plus y equals 2,400. Now, keep in mind, we want to be able to have the function we want to optimize or find the maximum or minimum in terms of one variable. So let's try to get rid of the y variable. Y is equal to 2,400 subtract 2x. And now we need to find the area. So the area is what's being maximized. The area would be length times width. Which would be x times y in terms of the diagram. But this is where we have two variables. So replace the y with 2,400 minus 2x. So x times 2,400 minus 2x gives us 2,400x minus 2x squared. So there's the quadratic function that represents the area. Now in a pre-calculus, you probably learned that you can find the maximum or a minimum for a quadratic function by finding its vertex. And since the graph opens down, the vertex will be a maximum point. So let's start to use calculus methods though, so that we can get an idea of how optimization problems work. So now that we have the area that we want to maximize, we need to find all the critical points of the area. So to find the largest area, which is referring to a maximum area, and determine the dimensions, we need to find the critical numbers. Of a of x. Alright, so we know how to do this from the last several videos. You take the derivative, and notice that the derivative will be 2,400 minus 4x. The derivative will always be defined, so you will not get any critical numbers from looking at where is the derivative undefined. That does not happen. But the derivative could equal 0 to give you critical numbers, and this would turn out to be x equals 600 when you solve the equation. So this is the only critical number for a of x. So we've learned several methods in this chapter. So you could use the first derivative test by making a sign chart for your first derivative. But now that we talked about in the previous video, there is the second derivative test. So let's take the second derivative, which is very easy because the first derivative was a polynomial. The second derivative is -4 for all values of x. So the second derivative is always going to be negative, which tells you that the graph of the area function will always open down, which is why it's a quadratic function, because it's a parabola that opens down. And the maximum will occur at the vertex, or in terms of calculus would be the critical point. So there's a local maximum when x equals 600. So the only critical number would give you the second derivative is negative, and so the critical point is where you have a local max, and this is 600 feet, which is the width, and the length was y, and y, if you substitute in 600 in for x, the length will be 1200 feet. So this is how optimization problems work. You want to find a function that needs to be maximized or minimized. In this case, it was the area. We found out the critical numbers so that we can find where a local max or local min occurs. We had x equals 600, and then we calculated the second derivative, and the second derivative was always negative, which means the graph is concave down. And the dimensions that maximize the area are 600 feet by 1200 feet. So let's try the next example. This time we are going to maximize volume, and you may have seen this problem in pre-calculus as well. This time we are asked to construct an open top box, so a box with no top, by cutting small congruent squares from each of the corners of a 12-inch by 12-inch sheet of tin, and then bending up the sides. And then the question is asking us, how large should the squares be cut from the corners to make the box hold as much as possible? So you can see from the diagram that's already been drawn that x will represent or denote the length or the width, because we are cutting out congruent squares from each of the corners. So it's the length or the width of the congruent squares cut from each corner. And these are in inches. All right, so now what are we trying to maximize? We're trying to have the box hold as much as possible, and that's referring to volume. So we need to maximize the volume. Of the box. And the volume of a box is length times width times height. Okay, so now we're trying to find a function, v of x, that represents the volume of the box. So notice that if you cut, the original sheet of 10 was 12 inches, and we are cutting x inches from each of the corners, so the length is 12 minus 2x. The width will be the same for the exact same reason. It's 12 inches, and we're cutting out we're cutting out x inches from each of the corners, and then the height will be formed from folding up the part that is left over from cutting out the squares. So the height will just be x inches. If you multiply these three together, 12 minus 2x, 12 minus 2x, and then just x, you can combine the 12 minus 2x and get 12 minus 2x all squared times x. So there's the volume of the box. Alright, so now the problem is going to proceed just like the last example. We need to find the critical numbers. So we couldn't find the vertex for this function because it's not a quadratic function. So we need to use calculus here. So let's find the critical numbers of the volume by finding the derivative, first derivative. Product rule, the power rule, and the chain rule. So first function times derivative of the second, 1. Second function times the derivative of the first, 2 times 12 minus 2x to the first power times negative 2. And if you simplify this, it will come out to be 12 minus 2x is in common with both of the terms, and you'll have a 12 minus 2x from the first term and a negative 4x from the second term. And this will simplify even further to 12 times 6 minus x times 2 minus x. So again, notice that the volume is defined for all real numbers. So this it's undefined, that never happens or never occurs. But obviously, if the derivative of volume is 0, we have two critical numbers. Looks like x equals 6 or x equals 2. So two critical numbers for v of x. So again, we can either use the first derivative and construct a sign chart and determine if x equals 2 or x equals 6 is a local max or local min. But let's calculate the second derivative and use the second derivative test once again. So remember how the second derivative test works. You take the second derivative, and to calculate the second derivative from the first derivative, we're going to use the product rule. So first function times derivative of the second, negative 1, plus the second function times derivative of the first, which is also negative 1. And then simplify, and you'll find that the second derivative is 24x subtract 96. So now, rather than setting the second derivative equal to 0, we're not interested in concavity or inflection points. We want to find out only what is happening at x equals 2 and x equals 6 in terms of concavity. So at x equals 2, substitute in 2, which is a critical number, into the second derivative, and you'll find out that the value is negative 48. Negative. So that means, using the second derivative, the graph is concave down at x equals 2. So there is a local maximum. So a local maximum when x equals 2. And this was, x was measured in inches. And we can actually calculate the volume by substituting 2 back into the original function. And you'll find it's 128 inches cubed. Alright, so now x equals 6. If you calculate the second derivative at 6, you'll find out it's positive 48, greater than 0. And that means the graph is concave up. So there's a local minimum at x equals 6. Inches. And if you substitute in 6 into the volume, you're going to find out it's 0. 0 inches cubed. Now that does make sense. If you cut out 6 inches from two corners, from each corner, you won't have any length or width remaining for the box because you cut out the entire side of the 10, which was originally 12 inches. So no volume. So how does this help us explain what has happened and answer the problem? Therefore, the volume is maximized of the box whenever 2 inches are cut from each corner. From the original sheet of 10. So that's what was being asked in the problem. It was how much should you cut out from each of the corners so that the volume of the box holds the most possible. They didn't actually ask us to find what is that volume, but we found it out already. It's 128 inches cubed. Alright, so those first 2 problems, they give us an idea of how optimization problems work. So now, example 3 is truly an optimization problem that you may have never seen from pre-calculus. In fact, this is what the project in the course is referring to. It's trying to minimize the cost when you're trying to construct a right circular cylinder, which is going to be a can. So example 3 says you want to minimize cost where the shape is a right circular cylinder. It is holding 1 liter of oil, and you want to find the dimensions that will minimize the cost of the metal to manufacture the can. Alright, so it's going to be a right circular cylinder. That means we're going to have a radius. So let R be the radius of the can. Which will be in centimeters, and I'll explain why in a second. And H will be the height or length of the can, also in centimeters. Alright, so the units are centimeters, even though centimeters doesn't even appear in the problem at all, is because 1 liter, if you remember the metric system, it's 100 or 1,000 milliliters, and milliliters is cubic centimeters. So the volume of this can that we're trying to form that minimizes the cost will be 1,000 cubic centimeters. So the radius is centimeters, and the height will also be in centimeters. And again, we need to find the dimensions. So we're going to find what the radius and the height are. That minimizes the cost. Of construction. So you might be wondering, there's no cost given in the problem. There's no how much does this cost in dollars and cents. Well, to minimize the cost, you're trying to minimize the amount of material that you're using, which in case of this can, you're forming the top of the can with material, the bottom of the can, and then also the body of the can. This is referring to the surface area. So in other words, minimize the surface area. Of the cylinder. Alright, so let's think about the surface area for a cylinder. We'll use capital S for surface area. So surface area is the area of each of the surfaces of the three-dimensional shape. So we have the top of the cylinder, it's going to be a circle. So that area is pi r squared. We're going to have the same for the bottom of the cylinder, exact same dimensions, so another pi r squared. And now the body of the cylinder, imagine that you are taking this cylinder and then you are cutting it. You are making a cut, and then you unroll the body of the cylinder, and it's going to form a rectangle. So let me just draw a quick shape of what this will look like after you have the can rolled out or unrolled. The length, or the height, is this side. And then you need to figure out how much will actually be unrolled. Well, it's the circumference of the circle. So 2 times pi times radius. And the area of the body of the can will be 2 pi r h. Now, notice again, this is just like example 1. We have too many variables. We cannot differentiate with respect to r or h whenever there's too many variables. So we need to have some way of replacing either r or h. So this is where the volume comes in. We also have information about the volume that the can will actually hold, 1 liter, or 1,000 centimeters cubed. The volume of a cylinder is pi r squared h, and this is equal to 1,000. It makes a lot more sense to replace the 1h than replace the r several times. So solve this equation for h. That way h will be in terms of r, and it'll be 1,000 divided by pi r squared. Okay, so that means replace the h in the surface area with 1,000 divided by pi r squared. So the surface area will be 2 pi r squared, combining the first two terms. And then the last term is 2 pi r times 1,000 divided by pi r squared. Which, if we simplify before we take the derivative, 2 pi r squared plus, looks like 2,000 divided by r. After the pi cancels out and one of the r's will cancel out. So now the surface area is in terms of only one variable, and I'm going to rewrite this so I can take the derivative a little bit more easily. So 2 pi r squared plus 2,000 r to the negative first power. And now you need to find the critical numbers. The local maximum or local minimum in this case is what we're trying to find, will only occur at a critical number. The only critical number we find doesn't necessarily mean it's a minimum or a maximum. It just means the local max or min can only occur at a critical number. So the derivative, where r is the variable, so s prime of r, it will give us 4 pi r minus 2,000 r to the negative second. So we need to find the critical numbers. Of the surface area. So let's rewrite the derivative so that we can identify what the numerator and denominator is of a single fraction. 4 pi r subtract 2,000 divided by r squared, and then find an LCD. Will give you 4 pi r cubed subtract 2,000 divided by r squared. And then I can factor out a 4 from the numerator. Pi r cubed subtract 500 divided by r squared. Okay, so then notice that the derivative is undefined if the radius is 0, if the denominator is 0. Well, this won't come into the problem because it won't be a local min or a local max necessarily, because the radius cannot be 0. So this is a critical number though, so we're going to plot this on the number line just to make sure it's not a local max or local min. But then you also have critical numbers where the derivative is equal to 0, which is when the numerator is 0. So ignore the 4, that will not come in with the critical number. If you solve for r, you're going to find that r is, that's the third power, not 2. you're going to find that r is the cube root of 500 divided by pi. Now, just to give some context of where this would lie on the number line, this is approximately 5.419. And it's centimeters for the radius. Alright, so this is the critical number as well. Now, before we move on, the last two examples we used the second derivative test. Here's the first derivative. If I want to find a second derivative, I would need to use the quotient rule, and then I would need to do some simplification to get into a single fraction again, and then find out the Hergert numbers, where is the second derivative undefined or 0. So I don't necessarily want to calculate the second derivative or worry about all that simplification. I'm going to use the first derivative test this time. So the graph is given, but we'll refer to that in a second. We're going to use the first derivative test this time. That way we can get an idea of how to use each derivative test in this section. So use the first derivative test for local extrema. Alright, so if you remember how this works, we had two critical numbers. The first derivative test says identify where the function is increasing and decreasing. So we made a sign chart or a number line. And this is for the first derivative. 0 was a critical number, and so was the cube root of 500 divided by pi. So let's choose test values of 1, and this was approximately 5.4, so let's use r equals 6 as our test values. Now, ignore, this is where the domain comes in. The radius cannot be negative for the can. We want to figure out, is the can supposed to be tall and really thin radius, or is it a really short can with a very wide radius? That will give us the minimum amount of cost, minimum surface area. So if you substitute these values into the derivative, s prime of 1 will be negative. So that means the surface area is decreasing when r equals 1. And then when it's 6, you'll find out it's positive, and that means the surface area is increasing. So looking at the sign charts, I notice that if I'm decreasing on the left side of a critical number and I'm increasing on the right side of the critical number, then there's a local minimum when r equals the cube root of 500 divided by pi, which we said was approximately 5.419 centimeters. So the can will have a minimum surface area, which will minimize the cost if the radius is 5.42 centimeters. And then we want to find out the dimensions. We still have the height. And the height is, now keep in mind, we solved for h earlier, and it was 1,000 divided by pi r squared. So if you substitute in this radius in for r, then you'll find out the height is approximately 10.839 centimeters. So this summarizes what we found. The minimum surface area is achieved or occurs when r is about 5.419 centimeters and the height is about 10.839 centimeters. And that minimizes the surface area, which will minimize the cost to construct this can, cylindrical can. So this will be a good place to stop. We looked at the first two examples that have connections from pre-calculus, but now we know how to solve the problems, solve the optimization problems using calculus. And now we've seen one problem that truly involves calculus methods to find the local minimum or local maximum of a function. In the next video, we're going to look at a couple geometry problems of finding the local maximum and local minimum, and a theorem that says if you only have one critical number, what does that tell you about an absolute max and an absolute minimum? So if you have any questions about any of the problems that we worked on this video, please let me know. Or as you work through the homework, please let me know if you have any questions. And I'll see you at the next video when we finish up optimization problems.